All right, well, my name is Stephen Spalding, and I currently work with OpenTable, where I do software development. I currently write back-end systems that empower great dining experiences, and that's all very fun and exciting. But today, we're going to talk about the Unix philosophy. There we go. So we thought we needed a catchy title because if free lunch isn't enough to get people here, at least good catchy titles. So Zen and the Art of Simple Software. So this is about the Unix philosophy. Probably most of you have heard of Unix. It's been around quite a while, but we might be wondering like what do we mean by like a Unix philosophy? And so that's a great question. And so to answer this question, we're going to take us back to a simpler time. So this is, we're going to go back to 1969. This is before the internet, long before Java or Python or JavaScript. This is even before we had Node.js. And so this was when a computer had 1,000 times less memory than the phone that's in your pocket, and LSD was still a legal substance. So let's see here. So Multics. In the beginning, there was Multics. Not quite the beginning, but we'll start here. Multics was an operating system that was worked on in part by Bell Labs. And one of the guys that worked on it was a guy named Ken Thompson. And so as you see, he thought it was way over-designed and overbuilt. And this was a common thought at the time. This thing is heavy, it's bloated, it's just got way too much code and complexity. The kernel of the thing was 135 kilobytes. And so to put that into perspective, the average web page today loads about 5 times that on every load. And just the jQuery library alone is twice that. So, but at the time, this was considered just way too much code. Like, we can't fathom this. So Unix was made in opposition to this, and so even the name Unix is a play off of Multics. Multics, the M stood for multiplexing information computer system, so Unix could be like uniplexing, and so a play on words. There was also a competing rumor that someone suggested it would be a castrated Multics, and so. Yeah, in any case, puns and obtuse acronyms have always been an important and cherished part of computer science. So, what is this Unix philosophy? A lot of it comes from some of the thoughts and ruminations of this Ken Thompson guy. And if you haven't heard of him, you might be familiar with his work. He worked for Bell Labs for a while and then for Google. He was instrumental in the Plan 9 operating system. Or if you've ever used regular expressions, the grep utility, UTF-8 character encoding, the Go language, then all these you've used his work. So the philosophy, if you just want to get your pizza and run, then I'll give you the TLDR of the whole talk, is that basically we emphasize short, simple, clear, modular, and extensible code. And so and then one question came up: is this relevant today? The philosophy of an operating system in the late '60s, and I don't know if that question's really relevant, but I think it is. And but as we go through this, maybe you'll pick out some nuggets that could be relevant for software that we're writing today. Most of this comes from a book by Eric Raymond called The Art of Unix Programming, and so it's online, and so if you're interested, that's where I stole most of this content. So let's get started. This is Raymond's list of 17 rules of the Unix philosophy, and that's a lot. But first of all, it's kind of like the pirate code. It's more like guidelines than actual rules, and we can kind of bake this down a little bit further. Like if you just had to break it down to one overriding philosophy, it's the KISS principle, right? Keep it simple, and this is a principle that is part of engineering, design for a long time. This isn't unique to Unix. And also, it's something that most of us are like, OK, yeah, that's a good idea. But I need to make this application actually do all these things. How in the world do I actually do this? So we can get a little bit more practical. So one also kind of overriding principle of the Unix philosophy is we write programs that do just one thing and do it well. And then we can connect those together to do overall what we want to do. So we'll actually take a look at these principles. We'll go through just briefly on each of these bullet points and see what we can learn. So the first is modularity. The idea that you take little pieces and connect them together to do something bigger. Linus Torvald talked about this, and he related it to the English language. We have just 26 characters in the English language, and then we put these together into words, and that communicates everything. And you contrast that with like Chinese, for example. We have a ton more characters. Each individual character also represents more complexity. It's an entire concept. But having each character be more complex actually means that you need more of them to express what you want to express as opposed to less. So it's complexity on top of complexity. Nothing against Chinese, but so that's something that Linus likes to say. And then also that helps us hopefully localize our problems into a bite-sized chunk that we can actually wrap our minds around. And then we can upgrade that part without totally breaking the overall scheme. The next main bullet point is clarity. That clarity is better than cleverness. So what do they mean by that? There's a few relevant quotes. There's a guy named Dijkstra, who you might have heard of. He's a pure scientist. And so he said, really, it's you want to avoid clever tricks. And as programmers, it's terrible because we love to come up with really clever solutions and tricks, but we need to resist that urge. So if you're debugging code, you might agree that debugging is probably twice as hard as actually coding in the first place, right? And so if you're coding something that is like absolutely, it takes all the cleverness you have to code it, then by definition, you are too dumb to debug your own code. So something to keep in mind. Ken Thompson, he said, when in doubt, use brute force. And what he's talking about is algorithms. And so there's all these really cool algorithms that we can use, and we can optimize something down so that it's order of n. But if you're not really sure, like if you need the performance, you're not sure if your n is going to be large, this advice is just use the dumb brute force approach. Because the gains that you may or may not get in efficiency and performance, you'll be trading that off for a lot of complexity in a lot of cases, and that's not always a good trade. So this is similar to modularity. We have composition. So you have these little modular parts. They need to be designed to connect to each other. Because if they're not designed with communication in mind, then you have to build everything as one big monolithic system, right? So in Unix, the standard way to do this is with simple text-based streaming interfaces. And so you may say, well, this is really limiting. If the only way we communicate, we don't have types, we don't have structure, it's just a simple stream of text. But on the other hand, when you have a really simple interface, it actually forces you to separate out your logic so that each module doesn't get down into the other one. If you're using remote procedure calls or more complex types, modules end up kind of reaching into each other, and so they're really actually all connected. They're not really modularized. And so one advantage of this philosophy is it forces separation. And so we can just give a little example. Like, let's say, like the cat program. If you're familiar with the cat program, it doesn't do a whole lot. It concatenates, and which it glues files together. The main thing we use it for is it just spits out a file. So I can just, boom, I just spit out all my slides. But then, like in Unix or in Linux or in its derivative OS X, we can pipe these programs together. And so let's say we want to search for like composition. So we can just by piping this into the grep utility, which it just does one thing. It all does is search through its input. We can do that. So maybe we want some context. So we can get the context of that, and then we can pipe it to something else. Let's say we want a cow to say this. There. So just by piping through these simple things together, we can make this combination that the creators probably never envisioned, and make a new program that does something different. And then let's say we can do something even different. We can sort this, say. Then we have an upside down cow that talks like Yoda. But so anyway. So that's just an example in Unix land. But then you think, okay, this is great, but does this have anything to do with the applications I'm writing? Well, it can. Like the principles of simple interfaces, and also the idea of pieces that do one thing and communicate. That starts to sound a lot like microservices, which is a buzzword of the day. And so this can kind of inform how we do that. Or it could be within your program. You can write, say, pure functions that just operate on an input and spit out an output, and then compose those together using some sort of glue. You could call that pipes. You could call it monads. You could it could look different ways, but you can use these same principles. Let's see here. And then the idea of designing your program from the start to communicate with a web app, that could have to do with making the API front and central before even your user interface. Think about, okay, what's this API like, and use that for your user interface. So that gets us into separation, where, like we were saying, you separate your mechanism from your user interface or from your policy. This also sounds a lot like the MVC idea, model, view, control. You separate your models from your views, like you do in a lot of frameworks and Rails, for example. There's another way this could look is, say, write a bunch of little C utilities that do something simple and glue them together with a higher level scripting language. This is what the Emacs text editor does, if anybody uses Emacs. It has a Lisp high-level interpreter that glues together these text editing primitives. And another example is Git. If anyone uses Git for version control, Linus used this methodology to write Git. He has a library of little functions, and then connects it together with a scripting language called Bash. And that's makes a very useful utility that we use called Git. And he even separates out these functions into lower level ones that users don't even use. He calls that the plumbing. And then some of the higher level ones that we're used to using, commit and push and whatnot, he calls that the porcelain. So he separates the plumbing from the porcelain, which is a reference to like a toilet's made of porcelain, but it's the human interface to the plumbing. That's Linus Torvalds analogies. But so also this separation makes things easier to experiment with, and also easier to test when you have these little pure functional modules that you can glue together. So simplicity. This is the fifth principle, but it is kind of an overarching principle. There's a few relevant quotes. I like this one. It seems that perfection is reached not when there's nothing left to add, but nothing left to take away. And to me, that speaks a little bit of the Zen that we're talking about. And it's kind of a Zen in that it's something that we're kind of reaching for, but is completely unattainable. But that's okay, because we can still kind of think like that. And this is Antoine de Saint-Exupéry, who's not a computer scientist at all. He's a pilot and a author of children's books. But it's still relevant, I think. And so Linus Torvalds likes to talk about simplicity. And a point he makes is that simple isn't easy. Also, Rich Hickey likes to say this. He's the author of Closure Programming Language. And so it can be actually difficult to make something simpler, but it pays off in the long run. So, next rule is called parsimony. I had to look up the word parsimony because I had never heard that word before. But it has to do with basically stinginess, and you want something small. So basically, only write a big program if you have to, and it is big in the sense both of the volume of code or just how complex it is. This is kind of redundant with some of the other points, but it's a distinct point. But it gets harder to maintain. And also, if you have just a large body of code, it's going to be a lot harder emotionally just to throw this away and to start over. And so, so when you can, do more thinking so that then you can have less code. Another quote by the venerable Dijkstra. It says we should keep our programs down to the size of something that humans can hold in their head. And then in the same talk where he made that comment, he said basically that we shouldn't be debugging, really we just shouldn't write bugs. And so, that's simple enough, right? So, I mean, I'm sure you don't write bugs now because we're all excellent programmers. But in case you're in doubt, don't write bugs. When in the context of he was saying this, he was actually kind of serious, and he was saying basically the way you do this is just write simple little functions in a simple way that you can completely understand what's going on, so that you don't have to rely on your tests. Which gets us to what he has to say about testing. He's saying the normal way to write programs, you write a program and then you test it. Nowadays, we do TDD lots of times. Maybe you write your tests and then you do your program. Either way, his point is your test will tell you that there are bugs, maybe, but it doesn't guarantee that there aren't any bugs. And so you can't rely on tests. The only way to know if your program's correct without relying on tests is to actually have it small enough so you can understand what it is doing. So, a few more points. Transparency, and they basically make it more lucid what is actually happening in your code. It's pretty straightforward. And robustness. Of course, we want our software to be reliable. Duh. But a lot of times, in order to actually make it reliable, it has to be simpler. And Tony Hoare, who's also one of the grandfathers of computer science, said the unavoidable price of reliability is simplicity. So, next point, representation. So this one's kind of interesting. He said you should fold knowledge into your data so your program logic can be stupid and robust. And so we have complexity we have to deal with. Our programs have to deal with complexity. But as much as you can, if you can push that into your data and then deal with that with simpler logic, lots of times it's a guideline that can work to give us simpler programs. Another of the principles is least surprise, and this isn't unique to Unix, but it's kind of an interface design thing. You should follow standards where there are standards, write interfaces that users are used to, and sometimes what's worse is you have an interface that almost works the way users are used to, but not quite. Like maybe you in the browser you tweak the way scrolling works. And so like you're trying to scroll a page and it's kind of like what scrolling is supposed to do, but not quite, and it's just really frustrating. And so why do we do that? Yeah, don't do that. Silence. This is especially applicable to actual command line programs where the output is the output, like something that you could actually feed into another program, so you don't spit out a bunch of stuff there that's not necessary. If there's an error, okay, there's an error, and let's talk about that. If not, just put the output you need. And so this, possibly could be relevant to API design. I don't know, but in any case, that's one of the Unix principles. Then repair. So this kind of relates to robustness, and basically it's saying on your input, try to make sense of what's being sent to you. Try to be a little bit tolerant. But then if you can't make sense of it, don't try. I mean, if you know there's ambiguity there, just go ahead and explode and say this is bad. And so one quote about this will be liberal in what you accept, conservative in what you send. And so when there is a standard, emit that to the standard. So if you're generating HTML, for example, go ahead and generate HTML that is correct and to the standard. Even the browser will take whatever crappy, malformed HTML you send it. But on the other hand, when you're parsing it, offer some leeway where it's not ambiguous. Economy, this is not a very controversial maxim today, I think, that machine time is cheap. Go ahead and let the machines work, and so that humans, we can use higher level languages. What's interesting is that this was a principle even in 1969, when computers were a whole lot slower than they are today. And even then, they were saying, hey, let's let the computers do the work for us. And this is related to the principle of generation. And probably the way we might express this today is along the lines of don't repeat yourself. And so if there is a block of code that would be repetitive, then you write code that does that repetitiveness for you. And so that's pretty straightforward. I think most of us agree with that. Now, optimization. Optimization is something that we, as engineers, we love to do. And I think we all know that premature optimization isn't a good idea, but then still, for some reason, we still do it. But let's see. There's another great quote by Knuth. You might have heard of a pure scientist named Knuth. If you optimize everything, you will always be unhappy. So that's all we have to say about that. Diversity. Basically, distrust all claims of the one true way, whether it's object-oriented programming that will solve all your problems, or functional programming that will solve all your problems, or the Unix philosophy that will solve all your problems. Just look at the problem you need to solve and figure out the simplest method that will get you there. And so always adhering to a particular philosophy isn't necessarily the way. And then finally, last one, extensibility. As Raymond said, design for the future. This will be here sooner than you think. But one way we can apply this is use versions. Versions in, for example, in file formats in Unix land, or in our APIs. Version your API because it's going to change. You're going to change your API, so just go ahead and plan for that ahead of time. And I think that's about it. So in conclusion, to quote the Doge, so Unix, such simple, wow. Thank you. All right. And